The last talk of the session will be by V.S. Secker, and all I know about him is that he's a 19th year PhD student, so 19th year. I'll have to talk to his advisor later on today.
All right. Thanks, Theo. Yeah, so I am a 19th year student, except that they can't fire me now. All right, so I'm actually going to talk about something that has been frustrating me for every one of those 19 years. And we might have a potential solution to solve that problem, which is the non-availability of data to drive the research that we do in this community. I think you probably heard like Henning's talk, his keynote also talked about the non-availability of data being a fundamental stumbling block for a lot of key research contributions. So as I said, this is joint work with the crew at CMU. Yu Cheng and Zinan were the PhD students who primarily led it, and it's a collaborative work with my colleague Julia Fanti. All right. So the context for this work, and many of you in this room know this, that the network traces are a very, very critical part of what we do at SIGCOMM'. Right? It drives a whole bunch of applications, whole bunch of use cases in understanding traffic, understanding patterns, modeling and predicting what happens, algorithm evaluation, what kind of new buffer management, new kind of machine learning things to do, as well as sort of security and resilience and so on. So data is everywhere. Data-driven research is everywhere. We're all doing sort of a lot of data-driven research. But here's the fundamental pain point for us. Now, we have a reproducibility crisis in academia. Especially, there's a bunch of industry track papers, industry papers, and so on, even academic papers, that are fundamentally not reproducible because that data is not available. Right? We don't make our data sets available. Like many of us are putting our code available, which is great. Open source has solved some of the code reproducibility crisis, but now data has become the fundamental stumbling block. And that lack of data availability means that we cannot reproduce results that we present at SIGCOMM'. And not just that, there is also a collaboration crisis, right? Unless I go physically sit in one of these companies, or my students go and intern there, it's impossible for us to collaborate with these companies and work on proprietary data sets at scale that the corporations have. And again, it's a frustration for the companies as well that many collaborative opportunities with academia go untapped for them. And if you're worrying, OK, here is just an academic who's ranting about this problem, why only academia cares? This is not just an academic problem. This is actually a problem for networking vendors as well. Throughout their product lifecycle, many people are doing network analytics, and they're increasingly finding that the fact that they cannot store or access historical traces is affecting what they're trying to do. For example, a data science team cannot build good, robust models for their networks or for their ML products because they don't have a lot of data. Similarly, when customers come and complain and say, hey, look, I have a problem with your product, they are unable to reproduce the customer problem because the customers are no longer sharing traces. And this problem is getting worse, right? I mean, we are in Europe, right? GDPR has been pioneering in terms of like privacy regulations, but those kinds of compliance and regulatory concerns are only getting worse. Worse for the better, but it's also making life hard for us to reproduce customer problems and so on. So this is a pain point across industry and across academia, this pain point that we are unable to access data, unable to get data sets of network traces, and that's sort of been the status quo for us. So our vision as part of the NetShare project is basically to sort of get away from the status quo and potentially solve this problem. Okay, this is the first step at trying to solve this problem. And what we're doing in NetShare is, given a data set of header traces, again, we're starting with headers, packet and flow header traces. That, again, very, very common, very useful for a lot of networking use cases. You take that as input. You can provide and say, OK, here are the kind of network properties, fidelity properties I care about. Here are the kind of privacy properties I care about. Like, I don't want my IP address to be revealed. I don't want this particular distribution to be revealed, and so on. And somehow, NetShare can now generate high-fidelity, privacy-preserving, synthetic network header traces, right? From this PCAP, from this flow header trace, I can now generate something that looks and feels like the original and preserves privacy, preserves the fidelity properties that you can then use for any of your downstream tasks. Now, because it's a PCAP, because it's a flow header trace, it looks and feels like what you would have had otherwise. So it's a very, very low-friction way for both academia and industry to use that data. And the hope here is that by doing this, you can actually sort of dramatically reduce the test and development time, reduce the frustration, improve reproducibility, also sort of accelerate your development time for new products and so on. Okay? Again, this is sort of the vision, right? So yeah, this is the first step towards getting this vision of enabling data sharing in our community, both academically as well as from an industry use cases. OK, so how do we do it, right? So I'm actually going to tell you what's the secret sauce to actually get NetShare to work in practice. To that end, I'm actually going to start by giving a little bit of background on something that sort of came out from the machine learning community in 2014, this idea of like generative adversarial networks and why they're exciting. Now, by the way, so we've all been looking at synthetic trace generation. There's a bunch of papers here to talk about, hey, I've handcrafted network simulators, I've handcrafted stuff, so why GANs? Now, here's sort of a high-level taxonomy of prior work. Most of the time, again, there's many, many decades of research in networking on trying to generate synthetic traces. And I'm sure every one of you who's ever written a SIGCOMM' paper or any other kind of networking paper has written a traffic simulator for yourself, right? It's extremely painful. You can use simulations. You could use like sort of, I saw like Poisson or other kinds of like statistical models. Getting those to work and actually mirror the properties you want in a real-world trace is exceptionally hard. It requires a ridiculous amount of human effort, a ridiculous amount of knowledge, a lot of domain expertise to actually get it to work. Now, there are some emerging machine learning approaches, including our own work earlier on time series models. They're promising, but they don't quite work off the shelf for network traces, right? So we are a unique beast. We got to believe we are a unique beast, and we are. Network traces are a unique beast that off-the-shelf machine learning just does not cut it. Now, I'll give you some very brief background on GANs, and you've probably heard of this, all these things about like deep fakes and generative adversarial networks. The really cool thing that they give you is the ability to take a corpus of data and then produce hyper-realistic copies or samples from that underlying distribution. Now, the most successful application of GANs has been in images, right? OK, I can produce like fake celebrity images. I can produce like fake cars and whatnot. But sort of stepping aside from the sort of the coolness factor and the visual demonstrations that those folks have, the underlying technology really is what it's able to do is learn high-dimensional correlations in underlying data sets and features without much human expertise. And that's sort of the excitement about GANs. But again, most of the use cases now are like trivial or funny or whatever, mostly for like a flash. I've not yet to see a good use case for it. So we're actually trying to say, can we actually take this very cool idea and put it to a good use for us, right? And that's really the motivating question for us. I don't care about generating fake celebrity images. That's not useful for networking or anybody. But what I really want to do is, can we take GANs and generate high-fidelity synthetic network header traces that provide good fidelity, that is representing what the original data was, scalability. Of course, I don't want to spend like several years running this on a 1,000-cluster GPU. OK, then basically that is forever. And then privacy trade-offs. Obviously, if you want to incentivize people to share, privacy has to be sort of upfront. All right. That's really sort of the motivating question behind NetShare and the vision that we're going after. And I'll tell you why this is challenging and briefly highlight some of the key ideas that we had as part of this project. And again, I won't have time to go into all of the ideas, but you should definitely read the paper. OK, so before we get started on like what are the cool ideas we came up with, it's useful to think about a seemingly natural strawman solution. So imagine anybody out there, and many people are doing this. You've read about GANs, and you say, hey, this is a cool idea. How do I take GANs and use it for network header traces? OK, so imagine you're a first-year PhD student. You read about GANs and say, what do I do? The most natural formulation, and it turns out many other sort of competition is actually doing this, you take a packet trace, like a PCAP, you model it as a table or a comma-separated file, a CSV, right? And then you basically say, I throw what are called tabular GANs. So these are GANs especially good for tabular or comma-separated CSV-type data sets. And then you say, hey, why not? Take each PCAP, run it through a tabular GAN, generate synthetic trace, and we are done, right? This would be the off-the-shelf. I did machine learning 101, do this. Now, it turns out, I mean, ideally, we would have liked this to work, right? Then we can all go home. There's no SIGCOMM' paper if this works. Unfortunately, that is not the case. There is a SIGCOMM' paper here because this actually does not work. And there's a bunch of fundamental challenges in getting this to work. So one is it actually does not satisfy the kind of fidelity properties, temporal properties we care about as a community, right? So there's header field correlations, temporal properties it does not capture. it is very bad at capturing fields like IP addresses and ports that have what are called like a large support or a large domain of values. There's, of course, scalability challenges, right? I mean, most machine learning papers don't tell you the cloud cost that they have, right? How long did it actually take to train this particular damn data set? And finally, there's also like privacy fidelity trade-offs. But again, I'll encourage you to go read the paper for that. I'll talk about some of these challenges and how we overcame them. So the first challenge we observed, for a lot of us, what we care about are things like properties at a flow or a session level, right? Things like the flow size, inter-arrival time within a flow, and so on and so forth, or the size of a flow and properties like that. And it turns out, if you model this PCAP basically as a table with independent rows of entities, and that's the abstraction that you feed into a GAN, it actually does really terribly. And in fact, these are all like sort of strawman solutions, and other people who have tried to use this tabular approach to generate traces. Things like tabular GAN, CT-GAN is a very popular tabular GAN approach. There are a number of other existing approaches out there to generate these packet traces. But really, you'll see that if you think about the CDF of packet sizes or flow sizes, it actually does not capture this correlation very well. Okay? So our insight here was that this flow is a very critical abstraction, right? We just don't think of packets as being independent. They come from some sort of flow generative process. The flow is important. So our first insight was like, OK, this is a bad idea to view this as independent rows or just as a table. But really, the right abstraction to think about this problem is what we call a time series GAN. And really, what you want to do is think about the flow ID and a sequence of packets associated with that particular flow ID. When did it arrive? What was its size? What are the headers, and so on? And that's actually something called a time series GAN, right? You're generating a combination of metadata and measurements associated with the metadata. That's something we call a time series GAN, not just a tabular GAN. And that's important, right? That's a much harder problem, but that's the right abstraction for our domain. Because we care about sequence. We care about the sort of patterns within a flow. And the time series GAN is the right abstraction for that problem. So what we end up doing is we take a large trace, or say a PCAP trace for a day. We kind of merge it and create these flows. And then we create like a flow-based abstraction of, OK, here is the flow ID, in our case, the IP5 tuple, and then the packet arrivals for that particular flow ID, and then give it to a time series GAN, in contrast to this approach of looking at each PCAP and giving it to a tabular GAN. Right? So we sort of explicitly reformulated this problem as a time series problem. The other challenge we found, and again, this is very common, is if you think about the fidelity versus privacy scalability trade-off, existing solutions, including sort of our own prior work on sort of doppelganger and so on, actually does very poorly in terms of the scalability fidelity trade-off. So here on the y-axis, we have like an average fidelity metric using what's called the Jensen-Shannon divergence metric. And the x-axis is the training time in terms of CPU hours. And we plotted all these sort of traditional solutions that existed in terms of the sort of the fidelity versus training time trade-off. Again, we don't have enough money to have a GPU cluster, so we actually ran it on CPUs. If you can donate a GPU cluster, I'll gladly take it. So we ran it on a bunch of CPUs, and these are like the CPU hour time for the time it takes. And again, that's a representative of the scalability challenge. GPUs might maybe reduce one order of magnitude, but it's not going to fundamentally change the game here. So poor scalability and fidelity trade-offs. And so what was our idea here? And we came up with this sort of pretty interesting system idea of like, OK, how do we actually make this more scalable? So we realized that we don't need to learn a model from scratch. We can do something in the machine learning world called fine-tuning, that you learn a baseline model, and then the subsequent iterations you can fine-tune. And once you have that baseline model, we can actually say chunk a trace into multiple chunks and run each chunk fine-tuning in parallel. So we get like two speed-ups. One, I'm not learning a model from scratch for every sort of epoch. Second, I can also parallelize the training across multiple chunks, starting with this sort of baseline initial model. Of course, a bunch of details to get here, like what is the chunking interval, what is the batching interval, how do you deal with model drift, and so on and so forth. Those are all sort of details we need to take care of. But this high-level idea of like fine-tuning plus parallelism gives us a pretty significant boost up in the scalability fidelity trade-off. Okay? Now, I'll sort of briefly summarize some of the other ideas. So sort of how do you encode the data is actually very important, right? if you give the bad encoding to a machine learning algorithm, it actually does really well, really poorly. And it also has implications for privacy. We actually have to come up with very careful encodings of like IP addresses and ports to preserve the data properties. And to improve the privacy fidelity trade-offs, again, everybody throws differential privacy as some sort of like magical weapon at this problem. If you naively use differential privacy on these problems, the fidelity is terrible. Okay, this is the thing that they don't tell you. So there's actually the differential privacy versus fidelity trade-offs are actually pretty bad. But the one idea to improve the trade-off is actually to use a small amount of public data and then retrain the model from that baseline model seems to dramatically improve the privacy fidelity trade-off for us. Okay. Again, I won't have time to go into detail all of this. Please sort of read the paper or come and talk to me. I can tell you more about the key ideas that we had. Okay. So our end-to-end flow looks like that. We take the original trace, reformulate it as a flow-based problem, then we use a time series GAN with this parallelized and chunking training with some optional sort of privacy inputs as parameters to the learning process. Okay. All right. So how do we implement this, right? Oops. All right. So we implemented NetShare. We ran it against a whole bunch of baselines. There's a slew of results in the paper that talk about various kinds of statistical properties of interest. So this is just a couple of traces. So one is a flow-level trace from the packet-level trace from Kaida, and another sort of university trace on NetFlow. The y-axis here is a metric called the Jensen-Shannon divergence. This is basically comparing two distributions and saying how similar they are. So lower is better. The x-axis shows like different attributes in your packet trace, right? Source addresses, destination addresses, ports, protocols, and so on. And of course, lower is better. And we compare NetShare against a whole bunch of other baselines. And across all these traces and the metrics that we tried, NetShare is like almost like sort of 46% better than the baselines in terms of the fidelity, in terms of the distance metrics. Now, OK, you might say, I don't just care about statistics, and you can sort of throw all statistics at me. I care about my downstream tasks. I care about my telemetry. I care about my anomaly detection. I care about those kinds of things. How well do you do there? So we also went sort of beyond just plain statistics and encoded a number of like standard machine learning tasks and anomaly detection tasks. In this case, we use the NetML toolkit from University of Chicago and ran a workflow where we use NetML and train on synthetic data and test on the real data. And again, we find that compared to all the baselines, NetML does really much better. And perhaps more importantly, and this is very important for us when we are doing like algorithm evaluation or pilot studies, NetShare preserves the rankings of your approaches. So basically, the rank correlation between algorithm set A1 to AN between the synthetic data and the real data is highly correlated. So now, if you use synthetic data and say, I'm going to run algorithm X in production, you have very high confidence that that is indeed the right approach to run in a real production environment as well. So that's actually a pretty useful result that we think. Okay. All right. Now, since SIGCOMM', we've spent a ridiculous amount of time. By we, I really mean my students, right? Kudos to them. The students have spent a ridiculous amount of time in trying to make this as usable and user-friendly as possible. So we've sort of released NetShare as a very simple-to-use Python package. It's very simple to install. You have some little bit of driver code, a little bit of configuration code to specify where your data is, what kind of properties you care about. And we can also give you a dashboard of the kind of metrics that you care about, all the statistical properties. In this case, again, that website basically hosts the dashboard. If you give us cloud credits, we can run it for you, but we don't run it just yet. But you can download the open source code and run it for you. So here, for example, we show a whole bunch of different metrics that are pre-computed in our library as part of the NetShare package that you can compare the real versus synthetic trace to validate for yourself visually how well NetShare does. OK, well, far from done, right? Again, this is not the end of the world. We do acknowledge that there's a bunch of limitations of NetShare. We don't yet do sort of more complex stateful protocols. Like we can't do TCP, we can't do payloads, we can't do session-oriented protocols, right? So again, that's sort of an interesting feature to add. We do want to support more kinds of downstream tasks, right? If you have like other kinds of downstream tasks that are interesting to you, both as an academic or as an industry vendor, love to talk to you further. We do want to improve the scalability much further, right? It's almost like I want to be able to run it on my laptop and get answer in 10 minutes as opposed to have a cluster of some sorts and run it for an hour. Now, the last question, and this is an open question, and again, this is something that we need to work on, is, again, this is just a personal bias. Everybody throws differential privacy as if it's the universal answer to all privacy problems. My belief is neither necessary nor sufficient for a bunch of problems in our world. So one sort of meta question for us is, like, if you talk to our vendors who want to share data sets, what are the actual privacy properties that these vendors and networking use cases care about? Right? It might have nothing to do with differential privacy. It might be a completely new model of privacy that we need to think about for our domain. And that's something we need to really think about much harder than in future. OK, all right, that's it. So again, as I said, this is like a 20-year-old frustration that I'm trying to solve. Right? I've been trying many, many times. And I think finally we think we have like one hammer that might work for us. This frustration of like not being able to access critical data sets from both vendors and other academics. And that's a reproducibility crisis. That's a collaboration crisis. That's also like a product crisis for many people. And sort of GANs are this, and again, more generally, deep generative models are a fantastic opportunity for us to revisit the status quo and change how we do data-driven research. This is just an early day of the feasibility and promise of using GANs and using NetShare. We have a ways to go. I mean, if you want to join us and contribute, more than welcome. There's like more work to do here than we have cycles for. We'd love to share the ideas, love to share the open source. It's also, again, we have GitHubs, we have open source. We'd love for us to join our community and contribute and sort of make this dream possible. And again, thank you. And again, all the work was done by my students. I'm just a pretty front end here. Thank you.
We have time for a couple of questions.
Hi, thank you, VS. I'm Leslie from Boston University, and thank you for the great talk. I have a question that is NetShare vulnerable to like attacks? For example, if you can train an adversarial gun to try to recover those data, to reverse it. Thank you.
Great question. And I think that gets into sort of the privacy properties, right? I think there are some intrinsic privacy properties that GANs satisfy. For example, in terms of membership inference, and again, there's also some theoretical research behind it. But more generally, if you have like side channels or if you have other kinds of like adversarial GAN things, we have to think about that, right? So how well you can predict. But again, in this case, it's not really, it depends on what property you actually care about. If you're trying to reverse engineer like a statistical property of saying, oh, I don't want to reveal my total volume, I don't want to reveal my sort of average IP packet size, that might be much harder. But that's also an open question for future research, right? One thing I would say is like most people don't know what privacy properties they actually care about. That's a meta problem we need to fix first. So yeah.
Thank you.
Hi, yes, Renata Teixeira here.
Oh, hey.
For Netflix. Thanks for the great work in tackling this challenging problem. So I've been thinking about all the research I've been doing with, looking at packet traces. Often, like for QA inference or application identification, we often need to understand the state, as you're saying, like you guys don't capture that yet, or correlations across multiple flows for the same application. Mm-hmm. So do you think that it's possible to add this capability and not lose the privacy?
Great question again. So just to sort of, if I understand, just to reframe the question, right? I think the question is, one is you need more complex cross-flow correlation and sort of stateful metrics of interest. That is something we don't support yet. That's a hard problem that we need to certainly go after. But again, I'd say the same question. If you can define the privacy property you actually care about, in this case, like say, well, for Netflix, obviously, de-anonymization is a big problem for Netflix. So that's actually something that you would care about. In that case, doing something like differential privacy or using some amount of public data to sort of solve that problem. Like we can get public data where we collect traces on our own and use that as a seed for doing that. That actually is a very good idea. And I think more machine learning people are also like warming up to this idea of like using public data plus private data. So that might be the way to solve that problem. That might be the more like long-term solution, is that enough vendors come together and say, here's a consortium data set that is public, and then everybody does like differentially private learning using that as a baseline model. It's almost like a foundation model type approach, but this is a foundation data set. That collective data set of a consortium data set might actually be the right way to solve this problem. So maybe more of vendors should get together and create that foundation data set, and that actually will, it's like this security, safety in numbers in that case, right?
All right, I'm going to have to cut this short. We're 10 minutes to the next session. So let's thank our speaker.
Thank you.
All right, we have a short 10-minute break, and then the next session will start. So I'll meet you guys back here in 10 minutes.